My name is Lynn Root, and yes, that is my real last name. My father likes to tell this joke. I don't know if he's being truthful or not. He's also a software engineer, and he learned CS in the military. So when he joined the Air Force when he was like 18, they're like, "Oh, hey, you're already in the system." I can't imagine like my 18-year-old like troublemaker dad like wreaking havoc in like the military's network. Anyways, yes, I am a site reliability engineer at Spotify. I've helped build infrastructure for our capacity management, our DNS system, as well as like the hostname generation. We have like a little Chaos Monkey-like service as well. Lately, I've been building infrastructure and tooling around digital signal processing pipelines. And I also do some internal like open source evangelism, getting other people to release their code. As a heads up, I'm probably going to take up the whole time. So if you have any questions for me afterwards, then let's hang out in the hallway after. All right, a quick question. Has anyone here read the SRE book from O'Reilly? Okay. I'm actually surprised it's not like 100%. Like the first one, the Google one. So basically, the TLDR of like every chapter in that book is use distributed tracing, it seemed like. So with the prevalence of microservices, where you may or may not own the services, all the services that a request might flow through, it's certainly imperative to understand where your code fits into the grand scheme of things and how it all operates. So there are three main needs for tracing a system. We have performance debugging, capacity planning, and problem diagnosis. And there are a lot of other like use cases for tracing as well. So while this talk will have a slight focus on performance debugging, these techniques can be certainly applicable to other needs. This talk is a bit jam-packed. Basically what I've done is like read and digested a lot of white papers. So I don't know about you, but this is kind of how I like to spend my Saturdays. So I'll first start with an overview of what tracing is and the problems that we try to diagnose with it. I'll also talk about some general approaches to tracing that we can use, and what key things to think about when scaling up to larger distributed systems. I'll run through some questions to ask, and then some approaches to take in diagnosing and fixing a service's bottleneck. And then finally, I'll wrap up with sort of an overview of the current tracing solutions for profiling performance. And yeah, as I mentioned before, probably won't have questions at the end, so we can talk afterwards. All right, in the simplest terms, a trace follows a complete workflow from the start of the transaction, or like a request, to its end, and including any components that it might flow through. So for a very simple web application, it's pretty easy to understand the workflow of a request. But then you add databases, and then you might separate the front end from the back end. You might throw in some caching, have an external API call, maybe behind a load balancer. And then you scale up to like tens, hundreds, thousands of times, whatever. Then it gets a bit more difficult to put workflows of requests together. Historically, we've been focused on machine-centric metrics, including like system-level metrics like CPU, disk space, memory, as well as like app-level metrics like requests per second, response latency, database writes, etc. Following and understanding these metrics are still quite important, but with these, there is no view into a service's dependencies or dependence. It is also not possible to get a view of a complete flow of a request, nor develop an understanding about how one service performs at scale. A workflow-centric approach allows us to understand relationships of components within an entire system, and we can follow a request from beginning to the end to understand bottlenecks. We can hone in on anomalistic paths, and we can maybe figure out where we need to add more resources. So here's like a super simplified example of a distributed system where we have like a load balancer, a front end, a back end, a database, maybe an external API or dependency. When we have complex and redundant systems, it can get particularly confusing to follow that request. So how do we debug a problem of a rare workflow? How do we know which component of the system is the bottleneck? Which function call is taking the longest? Is there another app on my host causing distortion to the machine-centric performance metrics? Do we have that noisy neighbor problem? So with so many paths that a request can take, with the potential for issues at every node and every edge, this can be mind-numbingly difficult if we continue to be machine-centric. So end-to-end tracing will allow us to get a better picture and address these concerns. So real quickly, there are many reasons to trace a system. The one that sort of inspired this talk is performance analysis. This is trying to understand what happens at the 50th or 75th percentile, the steady state problems. This will help us identify latencies, resource usages, and other performance issues. We're also able to answer questions like, did this particular deploy of a service have an effect on the latency of the whole system? Tracing can also clue us in on anomalistic request flows, the 99.9 percentile. Now, these issues can still be related to performance, but they can also help us identify problems with correctness, like component failures or timeouts. And then there's profiling, which is very similar to the first, but here we're interested in just like one component or like an aspect of a whole system. We don't necessarily care about like the whole end-to-end workflow. We can also answer the question of what particular component depends on what, and who it, like and what it depends on, like the child and parent dependencies. So with the dependence identified, we can then attribute particularly expensive work, like component A adds significant workload with disk writes to component B, which can be helpful when attributing costs to teams or services. And then finally, we're able to create models of our systems. And so with that, we were able to ask what-if questions, like what would happen to component A if we did a disaster recovery test on a component B? So there are various approaches to tracing, and I'll only highlight 3 common ones. The first is manual, and it's very simplistic. You're basically generating your own request IDs and adding them to your logs. There are simple things that can be done that can be added to a web service, especially one that does not have any dependents or dependencies that you don't have access to. You won't get any pretty visualizations or help with like centralized collection beyond how you typically handle your logs, but it still can provide a lot of insight. So like this is just some sample Python code, a very simple app where I've added like a simple UUID to each request as it receives to the header. And then I can log particular points of interest, like the start and end of requests and how it's handled, and anywhere in between. And then I can propagate those headers where I can. So yeah, 3 years ago, I got fed up with a particular service our team owns, and I essentially did exactly this. I did like printing debug statements, but essentially made me want a better way, hence this talk. I tend to do a lot of conference-driven development. So bring this just a small step further. If your app is like behind an Nginx installation that you're able to like manipulate, you can turn on its ability to stamp requests with an XRequest ID header, as you can see with the add header and then the set header. And then you can also very simply add that request ID to Nginx's logs. The next approach is black box tracing, which there's actually a really good white paper from Facebook about this. Black box tracing is essentially tracing with no instrumentation across any of the components. It tries to infer workflows and relationships by correlating variables and timing within already defined log messages. So from there, relationship inference is done via statistical or regression analysis. And so this is easiest when it's when there's centralized logging and when there's somewhat standardized schema to the log messages that contain an ID and a timestamp of sorts. And it's particularly useful when instrumenting an entire system is too cumbersome. Maybe there's too much coordination among all the engineers, or you can't otherwise instrument components that you don't own. As such, it's quite portable and has very little to no overhead cost, but it does require a lot of data points in order to infer those relationships. It also lacks in accuracy with the absence of instrumenting components themselves, and then it lacks the ability to attribute causality with like asynchronous behavior and concurrency. Another approach to black box tracing can be through like network level with the use of S-flow or NF-dump or IP packet data, which I'm sure the NSA might be familiar with. The final common type of tracing is through metadata propagation, and it's the approach that was made popular by Google's white paper on Dapper. The components are instrumented at particular trace points that follow causality between functions, components, and systems, or even within common like RPC libraries like gRPC that will allow you to add metadata to each call. And so metadata that is tracked usually includes an ID of some sort representing one single trace or workflow. And then there's also an ID for every point or span in that particular trace, like the request sent from the client and then request received by server, and then the server responds. And then with that, a span's start and end time. And so this approach is best when the system itself is designed with tracing in mind, but who does that? It also avoids the guesswork with inferring causal relationships. However, it can add a bit of overhead to response time and throughput, so the use of sampling trace limits that burden on the system and the data point storage. Sampling between 0.01% and 10% of requests is plenty to get an understanding of system performance. Although for some folks that actually might not be an issue, resource availability has come quite far since Google released the paper nearly a decade ago. When starting to have many microservices and scaling out to more resources, there are a few points to keep in mind when instrumenting your system, particularly with the metadata propagation approach as it's most common. There are 4 things, and I'll go into detail about each in a second. The first is identifying what relationships we want to track, essentially how to follow a trace and what is considered part of a workflow. And then there's how they are tracked. Since constructing and collating metadata to track causal relationships is particularly difficult, there are a few approaches. Each with their own like fortes and drawbacks. The third is how to reduce overhead of tracking. The approach one chooses in sampling is largely defined by what questions trying to answer when you're tracing. There might be a clear answer, but not without their own penalties. Or it might not even be an issue if you are not particularly resource constrained. And then finally, how to visualize. The visualizations needed will also be informed by what you're trying to answer with tracing. Okay, so what relationships to track? When looking within a request, it can take 2 points of view, either the submitter point of view or the trigger point of view. So the submitter follows or focuses on one complete request, and it doesn't take into account if part of that request is caused by another request or an action. So in this instance, evicting cache was actually triggered by the second request, but it's still attributed to the first request since its data comes from the first. The trigger point of view focuses on the trigger that initiates that action. where in the same example, the second request evicts the cache from the first request, and therefore the eviction is included in the second request's trace. Choosing which flow to follow depends on the answers that you're trying to find. For instance, it doesn't really matter doesn't matter which approach when you're doing profiling necessarily, but following trigger causality will help detect anomalies by showing critical paths. So the next is how to track, or what essentially is needed in your metadata. What this boils down to is that it can be difficult to reliably track causal relationships within a distributed system. So the sheer nature of a distributed system implies issues with ordering events and traces that happen among many hosts. There might not be like a global synchronized or synchronous clock available, so care must be taken when deciding what goes into crafting that metadata that is actually threaded through every trace. So you can use a random ID like a UUID or request ID header that will help identify causally related activity. But then tracing implementations must then use an external clock to collate those traces. In the absence of a global synced clock, or to like avoid issues like clock skew, looking at network send and receive messages can then be used to construct causal relationships, because you can't necessarily receive a message before it's sent. And a lot of tracing implementations use this simplistic approach. However, this lacks resiliency, as there is a potential for data loss from external systems, or the inability to add trace points in components that you don't own, that are owned by others. Tracing systems can also add a timestamp derived from like a local logical clock to the workflow ID, or it isn't exactly like the local system's timestamp. It's either like a counter or sort of a randomized number of some sort. With this approach, we don't need the tracing system to spend time on ordering traces it collects, since it explicitly has clock data. But then parallelization and concurrency can complicate the understanding of the relationships. One can then also add previous trace points that have been executed within the metadata itself to understand like all the forks and the joins. It also allows immediate availability of tracing data as soon as the workflow ends, as there's no need to spend time on trying to establish the order of the causal relationships. And as you can imagine, the metadata will only grow in size as it flows through the workflow, adding to the request payload. So basically, it boils down to this. If you really care about payload of requests, then a simple unique ID is your go-to. But that comes at the expense of needing to somehow infer relationships. You can add a timestamp of some sort to help establish explicit causal relationships, but then you're susceptible to potential ordering issues if a trace, or rather, when like data is lost, then like you're missing data and you're having ordering issues. It also doesn't really help with concurrent systems. You might add the previously executed trace points to avoid data loss and understand the forks and joins of a trace, while gaining immediate availability of trace data since the causal relationships are already established, but then you suffer in payload size. All right, on to how to sample. End-to-end tracing will have an effect on runtime and add storage overhead no matter what. For instance, if Google were to trace all web searches, despite its intelligent tracing implementation, it would impose a 1.5 throughput penalty and add 16% response time. Again, this might not be a problem for you folks now that there are fewer resource limitations than what we had like 10 years ago when that diaper paper was released, but everything still comes with some sort of a cost. I won't go into too much detail, but there's essentially 3 basic approaches to sampling. There's headbase, which will make random sampling decisions at the start of the workflow and then follow it all the way through completion. There's tailbase, which will make the sampling decision at the end of the workflow, implying some caching going on. Tail-based essentially needs to be a little bit more intelligent, but is particularly useful for tracing anomalistic behavior. And then finally, there's a unitary sampling, where the sampling decision is made at the trace point itself, and therefore prevents the construction of like a full workflow. So head-based is simplest and ideal for like performance profiling. Both head-based and unitary are often seen in current tracing system implementations. And I'm not sure if there's actually an open source tracing system that implements tail-based sampling, but there are certainly paid services out there that do that. Finally, what visualizations you choose to look at depends on what you're trying to figure out. So Gantt charts are popular and definitely appealing, but only show requests from a single trace. And I'm sure we've all seen this sort of type of graph when we look at our network tab on our browser's DevTools. And then we're trying to get a sense of where a system's bottlenecks are. A request flow graph will show workflows as they're executed. And unlike Gantt charts, they can aggregate information of multiple requests of the same workflow. Another useful representation is a calling context tree in order to visualize multiple requests of different workflows. This reveals valid and invalid path requests that they can take. And it's best for creating like a general understanding of a system behavior. So the takeaway here is a few things when you're tracing a system. You should have an understanding of what you want to do, what questions that you're trying to answer. Certainly, there may be other realizations and more questions that come from tracing a system. For instance, Google was able to actually audit its systems for security, asserting that only authorized components are talking to sensitive services. And I know that a lot of us engineers discover like really cool technology and that like fix all the things, and then we try and find a problem for it. But without an understanding of what you're trying to figure out, what the problem is, you might end up approaching your instrumentation incorrectly, or choosing a tracing system that is actually better for other purposes. So then once you know the problem, you can then identify the approach for causality, the tracking of relationships, whether trigger, point of view, or submitter, as well as your sampling approach. Another important question is, how much time can you put towards instrumenting your system, or can you even instrument your system? And this will inform your approach that you use to tracing, like black box or not. If you can instrument like all the things, then it becomes a question of what data should you propagate through the entire flow. And then finally, how much of the flows do you want to understand? Do you want to understand all the requests? Then be prepared to take a performance penalty on the service itself, or like need to deal with the storage of all that data. Is a percentage of flows okay? If so, then how you approach sampling should agree with the answer that you're trying, or is in your answer of what you're trying to address. So for understanding your performance, head-based sampling is fine, but when you're looking at anomalistic behavior, tail-based is better. And then if head-based is used, then there's a very real statistical probability that outliers will be lost. You also need to think about whether or not you want to capture the full flow of the request, or if you want to focus on a subset, and then this will also affect your sampling approach. Since I'm up here, I'm going to try and answer some of these questions for you. So with performance or steady state problems, you want to try and preserve the trigger causality rather than submitter to show the critical path to that bottleneck. Head-based sampling is fine as we don't need intelligent sampling. And even with low sampling rates, we can get a good idea of where the problem lies when we only care about the 50th or 75th percentile. Now, if we cared about the 99th percentile and anomalistic behavior, then we want tail-based. And finally, a request flow graph here is ideal because, again, we don't really care about anomalistic behavior. We want information of the bigger picture rather than looking into particular individual workflows. So most often when you're tracing a system, the problem will reveal itself, as will the solution, but not always. So I have a few questions to ask yourself when figuring out how to improve a service's performance. So one thing you can ask is, are you making multiple requests to the same service? Maybe you can batch those requests because network calls can be expensive. Perhaps your service doesn't need to be synchronous, or it unnecessarily blocks. For example, if you're like some big social networking site, can you grab a user's profile photo at the same time that you pull up their timeline, at the same time that you try and grab their messages? Is the same data being repeatedly requested but not cached? Or maybe you're caching too much or not the right data? Is the expiration too high or too low? And then what about assets on the front end? Could they be ordered better to improve loading time? Can you minimize the amount of inline scripts? Maybe make your scripts async. Maybe there's a lot of distinct domain lookups, adding time from DNS responses. And then perhaps you can use chunked encoding when returning large amounts of data. Or maybe you're otherwise able to have your servers produce elements of a response as they are needed, rather than trying to produce all the elements as fast as possible. Maybe even moving to gRPC might be an option to investigate here. So the final bit of this talk, let's see what tools are available to us. So we'll take a look at the open source standards or frameworks that the industry is lining around. We have open tracing, which has been around since the late 2016. And it's essentially a specification that allows developers to instrument their code without vendor lock-in. They do this by standardizing trace span IDs. One criticism is that they don't prescribe a way to implement more intelligent sampling rather than just simple percentage and setting priority. There's also a lack of API specification or guidance on how to track relationships, whether they're submitter or trigger-based. It's all pretty much just submitter. There's also OpenCensus, which is an open source project from Google, and it was released at the beginning of last year, and defines itself as more of an observability framework, not just tracing. So both Open Tracing and OpenCensus define an API for working with traces and spans, and both include like language-specific client libraries. But one noticeable difference is that OpenCensus publishes a standard library for each language, and it owns it, rather than Open Tracing having many people contribute to client libraries. OpenCensus is a bit broader in scope. Not only defines an API for tracing, but also includes a defined API for collecting and exporting of metrics. And with like a minute left, I'm going to try and go through the rest of this. There are a few self-hosted solutions. We have Zipkin, which has implementations in Java, Go, JavaScript, Ruby, and Scala. The architecture setup is basically the instrumented app sends data out of band to a remote collector that accepts a few different transport mechanisms, including HTTP, Kafka, and Scribe. When propagating data from a service, many client libraries only support HTTP. And Zipkin does provide some good visualizations, but there's no real visualization with latencies aggregated together. I'm just going to skip over this, sorry. I'll have a link at the end, I promise. And then Jaeger is another self-hosted system. So rather than the app library reporting to a remote collector, it collects on a local agent UDP and then sends it to a collector. I've got 30 seconds left. So that's like a TLDR of Jaeger, I'm sorry. And then an honorable mention, and then there are a couple services. There's Stackdriver from Google that uses OpenCensus, and there's a lot of gRPC support. It supports Zipkin. That's actually really easy to set up. And it has good UIs, but there's a lot of manual work behind them. And then finally, if I can get this out, X-Ray from AWS is actually really nice. There's a lot more support going on. And they have really good UIs that I really enjoy using. I'm just going to go towards the end. Sorry. All right, so everything is there with the slides, and pardon the solicitation, but we're hiring. One of the teams that we're hiring for is for observability, so if this interests you, you should stop by the Spotify booth. Okay, thank you.